Hello everyone, welcome to Study to Win Education. In this particular lecture of Metrology and Quality Control, I am going to share a knowledge on selective assembly. In metrology, I'll be talking definition of selective assembly, what is meant by selective assembly, how to perform a selective assembly in industry, what are the calculations related to selective assembly. I will take one numerical on selective assembly, and then what are the advantages of using the selective assembly. Similarly, what are the limitations of using a selective assembly. Lot to know. Let's start with a topic called as a selective assembly. Assembly is nothing but fitting one part into another. You can say it like when there will be one male component, there will be one female component, and these two will get assembled. This is assembly. There are three kinds of assembly. One is the make to suit assembly. Then there is something called as a interchangeable assembly. And then there is a selective assembly. In make to suit assembly, we will be making a part suitable for a existing part. Suppose we have a part with a hole. This is a part with a hole in it. I want a clearance fit in the hole. So I need to have a shaft which will get fitted into this hole and will give me a clearance fit. In that case, you already have a hole component with a hole, and then you want to make a shaft so that it will get fitted into hole with a clearance fit. In that case, you will not at all think about what is the tolerance, what is the dimension of this, what should be the dimension of shaft. What you will do, you will just try to match the diameter of the hole and then reduce little bit of diameter of a shaft so that there will be a clearance fit. That means basically you are just making a shaft which is suited for this particular hole. This is called as a make to suit assembly. You must have understood this is like a low end practice. In industry we cannot follow this. In some cases people might be following, but this is not something which can be widely used. So this is make to suit assembly. Then there is a well-known assembly called as interchangeable assembly. This is widely used. All automobile industries, all big industries uses interchangeable assembly. Interchangeable assembly means there are again two components. One is a hole component and then one is a shaft component. Here you have to give tolerance on the components. Hole component you will give some tolerance, and shaft component you will give some tolerance. And then you have to manufacture these components. You will manufacture so many components with a hole in it, and then you will have so many shafts. All these components are within the tolerance limit. There is some tolerance given on hole and there is some tolerance given on shaft, and these all parts are matching those tolerance, and those tolerance are designed to get a particular type of fit, whatever it may be, clearance, interference. Those tolerance are given such a way that when they get assembled, the required kind of fit will be achieved. When you are manufacturing the components in a given tolerance and randomly you pick any one of the component from a group, similarly randomly you can pick any component from a group, and when you assemble these two, you will get a required kind of fit for which these components or this tolerance of the components are designed. This is called as interchangeability. Means I can pick this component and this shaft, this hole, I'll get same fit. If I pick this hole and this shaft, still I'll get the same fit. This is interchangeable. This gives us an advantages of manufacturing the parts anywhere in the world. Anywhere you can manufacture and you can assemble it anywhere. Like I can manufacture the holes of a assembly in India, and I can manufacture the shafts in China, and when they get assembled, still I'll get the clearance fit. Even if I produce it in various different places, still I'll get the same fit. The reason is I have restricted the size of a hole and shaft by giving the tolerance on it. This is interchangeable assembly. Now if I want to talk about the selective assembly, it is a extension of interchangeable assembly. It is a special case, you can call it as a, where we will be making a group of these components. Like here also in selective assembly we will be giving some tolerance on shaft, some tolerance on hole, and then we will be producing it with large numbers as required, and then we will be dividing that numbers into groups. We will be dividing those parts into groups, and we will call those groups as ABC for holes and ABC for shafts. Then I have to pick a hole from a group. If I pick a hole from a group for assembly, then I should be picking a shaft from a group only. Then only I will get a clearance fit, or the required fit, you can say. If I am picking a hole from group B, then I should pick a shaft from group B. Then only I will get a required kind of fit. If I pick a hole from group A and shaft from group C, then I may not get a clearance fit. I will not get a clearance fit or the required fit for which the assembly is supposed to be done. So this is the idea. Now, how to make the groups, on what basis we should make the groups, why to make the groups, and all these questions you will understand as we move ahead with the lecture. This content you can read if you prefer, otherwise I'll come back to this content later on. I will try to teach the concept based on with a numerical. I will try to teach you this component. Let's suppose we want to produce a shaft with a tolerance of minus 0.15 to minus 0.05 on a basic dimension of 50, on a dimension of 50. Then we have a hole with a 50 dimension again and tolerance from 0 to 0.1. This is the shaft and hole dimensions, and we have to assemble this using selective assembly on a machine having process capability of 0.3. There is a machine, let's say there is a machine A which has a process capability 0.3. Understand what it means? This means this machine can produce a parts with 0.3 tolerance. If I try to manufacture the parts on this machine with 0.2 tolerance, then there will be more rejections. More rejections will be there. If I try to produce a part on this machine with 0.1 tolerance, then there is still more rejections. Rejections will go on increasing as we make the tolerance precise. For 0.3 tolerance, it gives a optimum rejection or a negligible rejection, so I can afford it. Like you can say, if I try to produce a parts with the tolerance of 0.3, I will get almost 990 accepted parts and 10 rejected parts out of 1000. If I produce 1000 parts on a machine A with the tolerance of 0.3, then I am getting 990 parts accepted and 10 parts rejected. This 10 I can accept, this 10 rejection I can accept, and I can say this machine is okay to produce a part with a tolerance of 0.3. If I try to produce a tolerance of 0.4 on the machine, certainly this will produce very good number of parts accepted. Maybe you can say 1000 number of parts will be accepted if I increase the tolerance. But let us not discuss this case, because then you are not utilizing the full capacity of the machine. 0.3 is the tolerance of a part a machine can produce comfortably with good number of accepted parts. That is called as a process capability. Process capability of machine is 0.3. That means I can produce a part on this machine with a tolerance equal to or greater than 0.3. This is the bottom line. We have a shaft here, we have a hole here. Let's check what is the tolerance of this. Tolerance can be calculated by upper limit of a part minus lower limit. Upper limit is you can say it is 49.95, and lower limit is 49.85. So the tolerance is 0.1 in this case. It is written here. Similarly, for hole case the tolerance is for shaft tolerance is 0.1, and for hole also tolerance is 0.1, but the process capability is 0.3. That means this particular shaft and this particular hole, if I try to produce on this machine which has a process capability of 0.3, then there are more rejections. Then there is more rejections. For 0.1 it is too much rejections, and the process is not economical. In that case, what to do? In this case, you either change the machine for production of these parts or use selective assembly to use this machine to produce these parts or to produce this assembly, such a precise assembly. I am here, what I am doing here, I am trying to make a assembly with a tolerance of 0.1 on a machine which has a process capability of 0.3. This is the beauty of selective assembly. I can do it with selective assembly. Let's check how to do it. Now in this numerical, hole tolerance is 0.1, shaft tolerance is 0.1. Since the upper limit of shaft is lower than the lower limit of hole, I can comment it like this is a type of fit is clearance. If you don't know about the types of fit and how to calculate the maximum and minimum clearance of it, then you can watch my video on types of fit, which is available in both language, Hindi and English. This particular video of selective assembly is also available in Hindi language. If you prefer Hindi language, you can watch that video. Selective assembly is used to produce a precise assemblies on a less precise machines. For that purpose, how to do it? Let's see. This is a we had a tolerance on shaft like 50 minus 0.15 to minus 0.05, and for hole the tolerance were 50, 0 to plus 0.1. These were the tolerance. What you have to do? You have to keep the tolerance, you have to raise the tolerance on a given component such that it will match the process capability of a machine. But raise it by using keeping one of the limit constant. So here I am keeping lower limit as a constant, and upper limit of a tolerance is raised, increased in such a way that the tolerance matches with the process capability of machine. So the upper limit of shaft tolerance from minus 0.05, it is raised to plus 0.15, and now the tolerance in this case is 0.3. Similarly, I have kept the lower limit of hole is the same, and upper limit from raised from 0.1 to 0.3. So the tolerance now in case of hole is also 0.3. This is the process capability of machine. Now this shaft with this tolerance and this hole with this tolerance can be comfortably manufactured on a machine with process capability of 0.3, because now tolerances are matching. This is what the first step you have to perform, and then you have to manufacture the number of components as required, and then you will get this kind of picture. This is a tolerance zone of hole, this is a tolerance zone of shaft. We know tolerance zone of hole will vary from 50.0 to 50.3, because tolerances on hole was 0.02 plus 0.3, and tolerance for shaft was minus 0.15 to plus 0.15. So this is the tolerance. Lower limit will be 49.95 for shaft and 50.15 for shaft. So this is how the hole and shaft will look. In between this there are all the holes will get produced. In between this there are all shafts will get produced. Then you have to divide the holes and shafts into number of groups, and number of group will be decided based on this formula. The formula is process capability divided by minimum original tolerance. Process capability in our case it is 0.3. Minimum tolerance in our case is 0.1, because originally shaft and hole had a tolerance of 0.1, then later on we have increased to 0.3 and so on, but initially the tolerance was 0.1. Make this division, you will get answer as a 3. So minimum 3 number of groups you should make to perform the select assembly. So 50.0 to 50.3 we have to make the 3 groups. Then groups will be like, you have to make equal groups with dividing the size in equal divisions. That means the first group will be 50 to 50.1, second will be 50.1 to 50.2, and the third is 50.2 to 50.3. And then you have to name those groups as a group A, group B, group C. And then there is a shaft. You have to make groups of shaft also, A, B, C, and then you have to write the group of shaft also. Here the dimensions are not visible. I'll write it for you. 50 minus 0.1 minus 0.15 to minus 0.05. This will be group A for shaft A, and the shaft in group B will have a tolerance of 50 minus 0.05 to plus 0.05. Here again the tolerance is 0.1, and the third group will be 50 plus 0.05 to plus 0.15. If you check any of this component from group A, group B and group C, either shaft or hole, you check any component, each component will have a tolerance of 0.1. Each component will have a tolerance of 0.1, which we originally wanted. And now what you have to do is simply pick any shaft or hole from particular group and assemble. Like if I pick a shaft from group A, then I have to pick any hole from group A, and then I have to assemble it. I will get a required kind of fit, clearance fit, and the required minimum and maximum clearance values will also get matched. Similarly, you can pick any hole from group B, and then you have to pick any hole from any shaft from group B. Still you will get clearance fit and the matching minimum and maximum values of it. That is the equal case for C also. Now let us perform one exercise. I am selecting a shaft from group A, and then I am selecting a hole from group A. Group A shaft has these dimensions. Group A hole has these dimensions. And then if you check, the tolerance is 0.1. The tolerance for hole is also 0.1, which we originally wanted. And then there is a type of fit is a clearance, because upper limit of shaft lower than the lower limit of hole. So this is clearance fit, and you can calculate the maximum and minimum clearance values. Maximum clearance is upper limit of hole, that is 50.1, minus lower limit of shaft, that is 49.85. You will get clearance is equal to 0.25. Minimum clearance can be calculated by lower limit of hole, that is 50, minus upper limit of shaft, that is 49.95. You will get answer as a 0.05. These are the values of maximum and minimum clearance, are same as it was required, or as we got it in original case, where we had a original tolerances, but then we have changed the tolerances. We have done a selective assembly, but still the output is same. We are still getting the maximum and minimum values, and the type of fit, everything is same. This is the beauty of selective assembly. This is how selective assembly is useful for producing a precise assemblies with a less precise machines. This is where a selective assembly is used, but it has some limitations also. The limitations in the sense, we have no control on manufacturing of the hole in between this tolerance zone. A hole will get manufactured anywhere in between the tolerance zone, still it is accepted. A shaft will get manufactured anywhere in between the tolerance zone, still it is accepted. We have no control in between it. That is to say, we have no control on the number of parts in group A, number of parts in group B, and number of parts in group C. Similarly, we have no control on the number of shafts in group A, number of shafts group B, number of shafts in group C. That means, if there is a large number of holes in group A and very less number of holes in group C, and there is a very large number of shafts gets produced in group C, and very small or very less number of shafts gets produced in group A, then the assemblies, limited assemblies will be possible, because there are so many holes with a group A and there are very less shafts in group A. So there are many holes in group A will be ideal, because that will not find a appropriate group shaft to get assembled. In that case, this is the difficulty that we may face. A second difficulty we may face is when the parts gets assembled in group A and group A hole, then group A shaft, and they get to those parts go to field and they get failed. Then we have to search for a particular group matching parts. If in the field, if the hole gets failed, then for the shaft A we have to look for a hole in a group E. group A, which is much difficult. In case of interchangeable assembly, you can pick any hole and assemble it with the shaft, you will get a right kind of fit. But here that is not the case. You have to particularly search for the specific group, and then only that part can be replaced. So this is like a disadvantage for the selective assembly. But in spite of these disadvantages, limitations, in a ball bearing industry we use this assembly, because you know how the ball bearing is. Ball bearing has a outer race, then it has a inner race, and in between it there are balls in a ball bearing. Then it has a cage also. Let's not consider the cage, but there are three main important parts. One is the outer race, then there is a balls, and then there is the inner race. These three parts are assembled using a selective assembly in a ball bearing industry. The reason is, we have heard that ball bearing has failed, but we never have heard that the balls of a bearing are failed, or outer race of a bearing is failed, or inner race of a bearing is failed. This we don't discuss. If something is failed in the ball bearing, we generally replace whole ball bearing. So we don't have a problem of searching for a inner race, outer race, or balls from group A, B, C or something. We generally replace assembly itself. So in selective assembly, in ball bearing industry, selective assembly is useful because we generally replace the assemblies and we don't look for the specific part in this industry. So where the selective assembly is used. Now let's move to the initial slide where we will read the text and try to understand or stronger the concept what you have learned. Selective assembly is economical approach for producing precise assemblies and thus improving the quality of assembled product. That means in selective assembly, with less precise machines, we produce more precise assemblies. So this is the beauty of selective assembly. It is economical because if machine is less precise, then it must be of low cost, and the assembly which we are making is very precise. That means quality of product is good. So this is what that sentence says. This sentence says that in this process the components of assembly are manufactured and then measured and grouped according to its dimension. The final product is assembled by selecting the component of each assembly from appropriate group to match the required specifications closely. This we have seen. This is a process of selective assembly. Then it is less costly than interchangeable assembly approach with tighter tolerance on individual components. It means selective assembly gives the higher quality assemblies using relatively less precise components. This also we have seen. And the last point is, it has been developed for manufacturing of component with very close tolerance on a machine which has very less or poor process capability. These all points can be well understood by this time. I hope you have understood the concept of selective assembly, and if you have any doubt you can write it in a comment section. If you need any improvement in the lecture, you can still write it in a comment section. And if you like this lecture, please hit the like button, share it with your friends, and if you are not subscribed to the channel, please subscribe it, which encourages us to make more and more videos. And thanks for watching this video. Have a great day. Thank you.